Good afternoon, everyone. We are delighted to have Mohammed Atiquzzaman among us today. He's our distinguished speaker. This is Ronnie Chaudhary. I'm the director for the Center for Connected Multimodal Mobility. So today he will talk about connected and automated vehicles. He is a professor in computer science or School of Computing at the University of Oklahoma. Miss Charlotte Riggs, our coordinator, will introduce Dr. Attiquzzaman. Charlotte.
Hello, and thank you all for joining us at our Center for Connected Multimodal Mobility Distinguished Speaker webinar. As Dr. Chaudhary had said, that today's speaker is going to be Dr. Mohammed Atiquzzaman. And so Dr. Attiquzzaman has obtained his MS and PhD in electrical engineering and electronics from the University of Manchester in the United Kingdom. He currently holds the Edith J. Kinney Gaylord Presidential Professorship in the School of Computer Science at the University of Oklahoma. Dr. Attiquzzaman is the editor-in-chief of the Journal of Networks and Computer Applications, the founding editor-in-chief of Vehicular Communications, and served on editorial boards of many journals like the IEEE Communications Magazine, Real-Time Imaging Journal, and the International Journal of Communication Networks and Distributed Systems. He also has co-chaired multiple IEEE symposiums and conferences like InfoComm, GlobeCon, and conferences for the National Science Foundation. Dr. Attiquzzaman has received multiple awards throughout his career, like the IEEE Communication Society's Fred W. Ellersick Prize, the IEEE Distinguished Technical Achievement Award for contributions in switching and routing, and NASA Group Achievement Award for outstanding work to further NASA's Glenn Research Center's effort in the area of advanced communications, air traffic management's fiber optic signal distribution for aeronautical communications project. He's the co-author of the book Performance of TCP IP over ATM Networks and has over 300 refereed publications. And his current research interests are in areas of the Internet of Things, wireless and mobile networks, ad hoc networks, and satellite networks, along with vehicular communications and optical communications. With that, we're going to go ahead and get started. If you have any questions, feel free to put them in the chat box. One of the moderators will go ahead and ask that. And then at the end of our session, we'll have a question and answer period. So thank you for joining us.
Thank you, Charlotte, for the introduction. As Charlotte mentioned, I'm a faculty here in computer science at OU at University of Oklahoma. And it's my distinct pleasure to be able to share my research with a distinguished audience like yourself. And also thanks to Ronnie for inviting me to this lecture series. I'm going to talk about vehicular communications in transportation systems in road networks. So give me a second, I'll share the screen. So this presentation is about increasing the road safety by communicating information among cars using vehicular communications, that means car-to-car communications. And I have been working in the area of communications for 30 years. That is my area of research. And recently, this has been my interest as vehicular communications or car-to-car communications has increased a lot of traction, has gained a lot of traction nowadays. So if we look at the auto industry, there are 4 trends in the auto industry, and it's sometimes people call it ACEs. One is cars are going to be automated, and you can already see automated driving cars. The second trend is the cars are going to be connected. That means they will be able to talk to each other, although you don't see it on the roads, but there are already some cars which have built-in communication capability among themselves. But at this stage, they only talk to cars from their own manufacturer because they have used the proprietary communication standards. But soon there would be a universal standard, which I'm going to talk about, which will allow cars to talk among themselves once the standard is approved. The third trend is cars are becoming electric, and you have recently seen a news item that by I think within 20, 30 years, a lot of these cars, or majority of the cars, are going to be electric. And then the fourth concept is the shared ride concept, which is Uber, basically. That's a lot of us are using Uber. So these are the four recent trends in the auto industry. And I am going to talk about mostly the connected vehicles. So all of us are familiar with autonomous driving, the cars which drive by themselves, and most of the car industry is heavily into it. And a lot of these car companies are already having their own autonomous driving cars. For example, Nissan has their own car, Toyota has their own car, Google has their own car, and all the big car manufacturers have their own automated driving cars. And the thing that makes these cars drive by themselves, there are two things. One is the ability to collect information around themselves. Number two is the algorithms they run to drive by themselves. So I'm going to show you what are the sensors that are being used to collect information from the surrounding. The people, when they drive, when we drive, we collect information about the from our surroundings by looking at the surrounding, by hearing, mostly by looking. So when we are looking, we can see all the stuff around ourselves. But in the case of automated driving, they have sensors, and there are different sensors to look at different things. So here are some examples, like there are long-range radars which can see further than the other types of radars, which are short distance. Then there are lidars, which you can see the red ones, which are shorter distance. Then there are cameras, which are even shorter. And then there are short to medium range radars. So there are different types of sensors which are collecting information from around the vehicle, which is being fed to a computer system, and the algorithms there help run the car. So this is just a pictorial view of a schematic view of a car with all the sensors, and you can see that there are sensors on the top of the car, which is all of you have, or many of you have seen in those self-driving cars. There's a thing which is rotating at the top, and that's a lidar. And then there are video cameras which look through the windscreen and look forward. There are sensors in the wheels which help you park, and there are sensors in the front and the back. All the places there are lots of these sensors which are collecting information. But if you look at a standard car, the cars we drive nowadays, they don't have those sensors which we are talking about, which enable a car to drive by itself. But they already have sensors. For example, there are side impact sensors. There are engine speed sensors which tell you what's the rotation or the RPM of the engine, and you can see it on the dashboard. And it has been there for ages. Then there are speed sensors which tell you the speed of the car. Those are displayed on the dashboard, and they have been there for ages. There is an airbag sensor, basically saying if the airbag is functioning. There is seatbelt sensor. If you don't wear it, it's going to beep. So there are lots and lots of sensors in a car already built in just a traditional car, normal car, not the automated cars. And some of them we get exposed to, like the speed sensor, the braking intensity sensor, which is ABS, the ABS sensor. If your car engages ABS, you can see a sign on your dashboard saying that it is engaged. And then there are road traction sensors. If you're losing traction on a road where there is ice, sometimes you see it displayed on the dashboard. But what I'm trying to say, there are a lot of sensors which are not visible on the dashboard, but they're actually built in the car. And some of these sensors can represent road weather conditions, how slippery the road is, what is the surrounding environment in the road. And those are the sensors which are usually not available on the dashboard, but they are inside the car, which are collecting information about the road weather conditions. So the concept of connected cars started 10-15 years back. And the objective is to connect all the cars wirelessly and be able, so that the cars are able to talk among themselves and share information. That is the objective of connected cars. And as you can see, if you could see the electromagnetic waves, that's what it would look like as you see on the left-hand side of the screen. And the important thing is to be able to connect them together so that they can share information. And in the connected car concept, it is not only the cars which are connected together, but the cars are also connected to the roadside infrastructure, like traffic lights, like parking lots, shopping malls. These are roadside infrastructures which don't move, in contrast to the cars which are actually moving. So as you can see on the top right-hand corner, there are two communication devices. One is the onboard device, or the onboard unit, which you can see on the left-hand side. And then there is a unit called roadside unit, which is shown on the right-hand side. And these communication devices communicate among the cars and the infrastructure. So basically, there are two devices which enable this vehicular communication, the onboard unit and the roadside unit. Now, the communication between the cars are wireless communication. Wireless communications has a very limited range. It can go half a mile, might be a mile, not more than that. So the communication between the cars are going to break all the time. So if you build a network among the cars, this network is called an ad hoc network, as you can see on the left-hand side. So if a car is further away from you, the message you are sending has to hop between the cars. And this is called routing in communication theory. So you send a message and it goes to the next car, and the next car relays it to the car in front of it or behind of it, and so on. So this is called an ad hoc network. The reason it's called an ad hoc network is this infrastructure or this communication network, which has been built between the cars, this is temporary because a new car can come in and be part of the network, or a car can leave and be out of the network. So it's not like a network we see in our building where we work, in our offices or at our homes, which are stationary, and it's not ad hoc, it's a stationary network. But this is a very ad hoc network. The network topology or the connection between the vehicle changes all the time. So that gives it a different flavor than the types of networks we are used to. And here you can see some examples of these two cars which are connected to the traffic lights, and they're also connected to the parking lot. And they're also, so they may be receiving information about the signal phase timing from the traffic lights, and they might be getting information saying that drive at 35 miles per hour, or information from the parking lot, there are 50 parking spaces available. So while you are driving, you are getting all this information through this wireless network. And the cars can also be transmitting their information to other cars, like the latitude, longitude, the speed, whether they're braking very hard, if they're trying to turn left or right, what type of vehicle it is it a car or is it a truck, what is the bumper height, lots of information you are actually transmitting to other cars, so that other cars also get a good picture of what is around or what type of cars are around. Now, having all this information flowing between the cars and the infrastructure is good and is possible nowadays. But the important thing is, how do we use this information? There are different types of applications you can develop. And this chart shows basically three types of applications. Safety applications, which are meant to increase the safety of vehicles. Mobility, which are helping the mobility of vehicles, like congestion and that sort of stuff. And then there are applications which can be built for environment, which will help the environment if you know about the information about your surrounding. And I'm going to highlight some of the applications. For example, the safety application which we have been working with is how to increase the safety of vehicles due to bad road weather conditions. So a typical example is, if there is sleet on the road, the car might be losing traction and is very dangerous for cars. And can we tell other drivers about this road weather condition. Before I go into that, let me explain some of the safety applications that can be developed. For example, there is a forward collision warning which is already implemented in cars, but not using vehicular communication. They are just using cameras and lidars and radars and that sort of stuff. Then there is a blind spot or lane change warning. If you are trying to change a lane and if you're in a blind spot, you can be warned saying that you cannot see the other side of the road, there is a car there. Then there are applications you can develop like do not pass warning. Then there are left turn assist. A lot of the accidents happen when you're taking a left turn. You're making a left turn and the car coming from the front comes and hits you because you cannot gauge the speed of the approaching vehicle. So in this particular case, as soon as you turn on the left turn signal, your car has information from the other cars. What are the other cars? And it will automatically tell you that don't make a left turn. It's not safe to make a left turn. So these are some of the safety applications you can develop once you get the information about your surrounding cars. And then there are a lot of other cars, other applications also, like the reduced speed zone warning. It will tell you that the speed has been reduced in the front, and you don't have to look at the signs on the road because the car dashboard will display that. And this comes from the map which is available to the car and from the information that are transmitted from the roadside units. And there are a lot of mobility applications you can see on the left-hand side, and I'm not going to go through all of them, but our project was mainly with increasing the safety of the cars due to bad road weather conditions. Here's an example of an application which can be enabled if you can connect the vehicles together. It shows a fire truck approaching a traffic light, and it can send a signal to the traffic light using this wireless communication, and the traffic light will make sure that it is green so that the fire truck can pass. So this is an example of an application where emergency vehicles can be given priority. So it's an emergency vehicle preemption application. And on the right-hand side, you can see another application which can be developed as soon as the car-to-car communication is enabled. You can see the car you can see the red car, which is label 1, which is on the wrong ramp. It's driving on the wrong side of the ramp, and it is trying to join a highway and in a ramp which is actually an exit ramp. So as soon as this happens, the red car's software knows about it because it has the GPS location. It knows where the car is, which direction it's traveling, and the driver has made a mistake. So it immediately transmits a warning sign or a warning message, which goes to the blue car, which is number 2, and the blue car relays it to the other truck, which is number 3, and that relays it further to the yellow car, which is shown in label 4, and that driver in the yellow car will get a message saying that there is a car which is coming in the wrong way, which is referring to the red car actually. So the yellow car can slow down or stop or take some actions to avoid the accident. So that is possible when we are connecting the cars, because as you can see, the red car is sending the message which is being conveyed to all the cars in the area. Here's another example of black ice detection sensor. This is real-time alerting other drivers of black ice. So the truck which is shown in green is losing traction, and that can be determined by the sensors built inside the car that's losing traction. As soon as it happens, it broadcasts a message to all the cars around that my car is losing traction. And within milliseconds, all the other trucks, the blue one and the red one and the yellow car, they will all get the message saying that this truck ahead is losing traction, and also show at which location is losing traction. And this is all possible if we can connect all the cars together. So if you look at the smart city challenge, which we see nowadays, there are a lot of elements in the smart city challenge, and I'm not going to go through all of them except highlight 2 of them. And one of them is the connected vehicles concept for a smart city. So the connected vehicle is a very important component of the smart city challenge. So if we look at these two concepts, one is the autonomous vehicle. That means the cars are going to drive by themselves by collecting information from the surrounding using cameras, radars, and lidars. And the other concept called connected vehicles, which means cars can talk to each other. If you combine the two concepts together, you get the concept of connected automated vehicle. So these vehicles are going to drive by themselves because they're automated vehicle, but they will get information from not only their surroundings, but because of the connection, they will get information collected by other cars around it. So the cars will have much more information than what it only can collect by itself. And additional information, of course, will help the car drive much better. So instead of one car collecting the information, this car will have information collected by a lot of cars around it. And that is a concept called connected automated vehicle, and that is the recent trend. So the future is the connected autonomous vehicle rather than just the autonomous vehicle or just the connected vehicle. So if I want to describe some work we have done at University of Oklahoma, Center for Intelligent Transportation Systems, this was a project we did with our SPTC, which is a UTC, just like your one. And so we looked at the vehicle crash statistics on roads and highways, and you know very well all the statistics: 33,000 deaths and 2 million injuries, and the cost of fatality is about 3 million. And these are all DOT data. Injuries 68,000. So this is very expensive. If there's an accident, if there's a fatality or injury, is very, very expensive. And this considers the cost of loss of income and all sorts of costs are involved in this. And we looked at the fatalities from tornadoes in Oklahoma, because whenever Oklahoma is in the news, it's usually a tornado. And if you look at the fatalities from tornado, it's about 7 in 1 year. But if you look at the number of people who are killed in road accidents due to bad weather-related conditions, is much, much more. As you can see, is 15. So although we hear about the fatalities from tornadoes, we don't hear about these fatalities coming from road weather conditions and accidents on the roads. So we wanted to reduce that number. That can we reduce this number due to road ice fatalities from 15 to whatever lower it is. And there are a lot of work which has been done in order to reduce fatalities on roads, like warning the drivers and putting salt on the road. All this stuff help. But another thing that will help is if we can alert the driver in real time. If we can alert the driver in real time, then we can take precautions, because a lot of these information which are displayed on the roadside, that there is a slick part of the road, is not real time. It can take a few seconds, or it can take minutes, but we are talking about milliseconds. That means a car which is losing traction will be able to tell the car behind it, immediately behind it, or the cars behind it, immediately within a split second, that I'm losing traction, which will help the drivers to slow down. So in order to do that, there are a number of things which are required. One is, can the cars collect information about its road weather condition? Number two, can this information be transmitted to surrounding vehicles? So we looked at the sensors which are there in the normal cars. We're not talking about high-end cars. And there are a lot of things, like there are information which the car collects, like brake status, brake system status. So as soon as you apply a brake, the sensor actually picks it up. There's traction control status. If the car is losing traction, your car actually picks up that information. And then there are ABS status. If the ABS has been engaged, the car knows about it, the sensor knows about it. The car is losing stability, the sensors actually pick it up. So these are all the information that the car already has about the road weather condition, because these are related to road weather condition, losing traction and ABS engaging, and all these are road weather conditions status. And then there are other sensors which pick information about whether your lights are on. So if your lights are on during daytime, probably it's a foggy day, or it's not, visibility is low. If the wiper is on, probably it's raining. Then if the rain sensor will pick up the rain, so it knows that it's raining. Then outside temperature, if it is below freezing, that is also road weather condition sensor. So what you can see on this page are all the information that the car sensors pick up from the cars and around it. If this information, what you can see here on this slide, can be sent to other cars, then they can form some sort of, they can actually figure out what the surrounding environment could be, the car 1 mile ahead of it is facing. And these are all real time we're talking about. These are all millisecond. It takes millisecond to broadcast the information to cars all around. So let's say if there's a black ice and the sensor picks up the black ice information, it can send it to other cars, which other cars can take action immediately, which means they will slow down. So how do we make this communication possible? And one of the standards which have been implemented in the communication area or vehicular communication area, and also heavily supported by US Department of Transportation, is called the Dedicated Short Range Communication, or DSRC. And this is a standard which has been developed by IEEE, just like the Wi-Fi standard you're using, which is also developed by IEEE. And I'm not going to go into the details of the standard, but it's using a 5.9 gigahertz frequency spectrum, and is very similar to the Wi-Fi, what you are used to. But the Wi-Fi actually is not, or was not designed for moving vehicles. It was meant for stationary devices like laptops, which you're not moving around with, or phones, which you're not moving around with. Might be you're walking, but that's a very slow speed. So this DSRC was designed very similar to Wi-Fi, but it has added advantage of being fast. Fast means if you are joining a Wi-Fi, is very, very slow. It takes a few seconds to join. But if you are in a road environment, whenever you join a road or a network which is there, then you must be able to join the network very, very fast. So it has a very fast joining protocol, is very secure. People cannot break into it, which means they cannot misdirect you and then you end up in somewhere else. It's very, very secure and is very reliable. And especially designed for moving vehicles, that is the important part. And this protocol says that you must transmit your car information, not all of them, but there are some messages, there are some information in the car you must send out to its surrounding 10 times per second. So every 100 milliseconds, you must send out certain information about your car. And the range is about 1 kilometer at 200 miles per hour. That's pretty reasonable range. For regular vehicles, it can go up to 300 meters because of the surrounding environment may not allow you the full range. But for public safety vehicles, the standard says you can transmit with much more power, so you can go up to 1 kilometer. So these are special vehicles. The safety vehicles have additional coverage, additional range. And the data rate can be from 6 to 27 megabits per second, which is pretty reasonable for car-to-car communication. And the latency is extremely low, 200 microsecond latency. And the standard is immune to extreme weather conditions like rain, fog, and snow. If you take a Wi-Fi in a rainy condition or a foggy or snowy condition, it may not work well, but this has been designed so that it works well in those conditions. So they're using a different physical layer and different encoding mechanism so that, and a different frequency range, so that it can penetrate through rain, fog, and snow. So as I said, the main components of the vehicular communication is the onboard unit, which is built in a car, and the roadside unit, which is attached to the infrastructure like the traffic signs and the parking lots. And you get information from the car's sensors using the onboard diagnostic reader. All cars manufactured in US in the last, I think, 20, 30 years must have this onboard diagnostic reader. The onboard diagnostic port is called OBD port, and you can buy a reader for $30, which you can connect to this OBD port, and it will give you a lot of information about the car. And currently, the information which are available from the car using this reader are mostly engine diagnostic information, where your engine is having problem and this sort of stuff. So when you go to the car mechanic, they actually put this thing in and collect information about your car to find out where things are going wrong. However, this port has a lot of other information which this reader cannot read because the car manufacturers are encrypting the information. And all the information I told you about the road traction and the brake status and ABS and all the stuff, a lot of them you cannot read because they're encrypted. But this port has all the information available, all the information that are collected by the sensors in the car. And if they are decrypted by the manufacturer, you can get a wealth of information about the car and its surrounding. So we have been, the Center for Intelligent Transportation System at University of Oklahoma has been working with the Oklahoma Department of Transportation and the Oklahoma Highway Safety Office for a long time. And we have been using the traditional methods to solve their problems. So we have a lot of the equipment that are traditionally used by Oklahoma Department of Transportation, as you can see, all these cameras and radars and all the stuff we also have in our lab, so that we can develop those. We can develop solutions for them, and we have also a number of cars. And then we thought of taking this new project for connected vehicles. So here is how we are trying to do it. On the left-hand side, it shows a road network, and you can see a roadside unit, which is one of the units I showed earlier. And you can see two of the cars, and they are connected using onboard unit, using the DSRC protocol, which is the wireless protocol, very similar to Wi-Fi that I described. And the vehicles can also communicate with the roadside unit using the DSRC protocol. And what we do is, whenever there is a vehicle which hits a slick spot, we transmit that information to other vehicles and also to the roadside unit. The roadside unit establishes a TCP connection to a server in our campus. We send it to our, which is connected to our Wi-Fi unit, of course. And Wi-Fi, through the Wi-Fi, we reach the global internet. And then we send it to the cell phone tower in Sprint. And Sprint actually broadcasts that information to the DMS, or the dynamic message sign, saying that drive slow because there's a slick spot. And all this stuff we're talking about is done in split seconds. So as soon as a car is losing traction, the surrounding cars get a direct message saying that the car is losing traction. Also, it shows up in a DMS for cars which are not equipped with onboard unit. And on the right-hand side is a display of the information we collect from the car engine using the OBD port. It only shows some of them. For example, the speed which you have collected, which you can also see on the dashboard, and the RPM which you can see on the dashboard. But this is the interface we designed just to show that a lot of information can be obtained from the car engine, which are actually not shown on the dashboard, but are available. For example, this is showing that the car is in a third gear. It's also showing that the lamp is in the high lamp position. It's also showing the steering wheel position. All this information can be collected from the onboard diagnostic port. The brake pedal information can also be collected. And we collected the information and just showed it on a display here. And on the right lower corner, you can see the information in numerical form. It shows the engine speed, the vehicle speed, the steering wheel angle, what is the angle of the steering wheel, how much fuel has been consumed, the odometer reading, the parking brake status, windshield wiper status. And in this particular case, it was true, which means that it is probably raining there because the wiper is on. And these are the software we actually developed for the application. And there are three components to it: the onboard unit, the roadside unit, and the dynamic message sign interface server, which shows the messages on the DMS. And the onboard unit, the transmission is of course DSRC between all the units. But between the roadside unit and the DMS is all TCP connection, the standard internet protocol. So on the onboard unit, we set up a socket and collect the information from the onboard diagnostic port. We receive GPS data, we receive data from the onboard unit. We connect all this data together and build a packet. WSM packet is one format for the DSRC. We form a packet with all the information collected by my car and transmit that to all other cars around, and also to the roadside unit. And the roadside unit will get the information, extract the information, and find out if there is a situation where we can warn the drivers. In that case, the roadside unit will set up a TCP connection and send a message to the DMS server. And the DMS server will, of course, display that message and on the display sign. So this is the structure of the software we developed in order to warn the drivers around us, and also to warn drivers by DMS messages for those drivers which don't have the onboard unit. This is just the sort of, these are some of the figures showing, or photos showing the sort of things when we're developing it. So you can see the onboard unit on the dashboard. The laptop is running the onboard unit software, which is going to run on the vehicle. And when it's completely developed and fully developed, you will not have the laptop. You don't have to keep on looking at the laptop while driving. It will be some sort of display, or you could be allotted to a slick road conditions by vibrating the seat or vibrating the steering wheel. But those are user interfaces that have to be designed. So what I'm trying to say is you don't have to have a laptop on your lap while you're driving to get all these warnings and messages. Sorry. So this is a sort of publicity that what Charter was saying. I run these two journals as editor-in-chief, Journal of Network and Computer Applications. And this shows one of the criteria of the journal, the impact factor, and we are pretty high up in the impact factor as among the communication journals. We are a Q1 journal in all the three categories that we are listed in. The second journal is the Vehicular Communication Journal, and this is a new one which has been there for about 6-7 years. Here also we are very highly ranked in terms of impact factor as compared to the other journals in the communication area. We are listed by SCI in telecommunications and transportation science and technology, and we are actually Q1 in both the categories. So please submit high quality papers. We are always looking for high quality papers for the journal. Thank you very much, and I'll be happy to answer any question you might have.
Thank you. So if you have any questions, feel free to put them in the chat and we'll read them out. Or you can also unmute yourself and just ask the question directly.
Dr. Atiquzzaman, I have two questions. One is for the infrastructure side. So when you're the roadside units, so you are collecting some specific data. So what should say speed advisory? The driver should drive at 35 miles per hour. So is there any standard associated with it, like for the onboard unit data, like the acceleration, position, location? Those are standardized, right? The messages by the SAE 2745 standard for basic safety messages. But from the roadside unit side, So you are generating different customized advisories. So are there standards? So there's some data that will be standardized, like the location of the RSU and so on. But the specific information that are messages, so are those standardized?
Yes, the communication between the roadside unit and the onboard unit, there are standard packets called WSMP packets. So you put all those SA messages inside those communication packets.
But if there's some customized, so that might be relevant to Oklahoma. So can you add? Yeah.
No, the DSRC is a universal standard, and it doesn't have any standard customized to any geographical region.
Okay.
But you can design your own. See, you have the SA message set that we are referring to.
Right, right.
And you can design your own message set also for your state.
Okay.
And it will just be put on the DSRC messages.
Okay, all right. So my next question is for the onboard unit. So the vehicle specific encrypted data. So you're able to get all those data decrypted and use it for your weather application. So did you have to do anything specific to get those data, encrypted data from all the vehicle related data, like specific vehicle, like steering wheel angle and the steering wheel height?
The steering wheel angle, the petrol level, the gas level, or how much gas is consumed, all these things, they are not encrypted at this time. And we are using Ford cars. We have a Ford SUV and a Ford, actually a truck. So we're using those two. And in those two, Ford did not encrypt those two information and the other information I was showing you. But the traction, for example, they encrypted that.
Right.
So we could not get the traction. So for our experiments, we just switched on the wiper, for example, to simulate the loss of traction.
Okay.
But we were talking to Ford, and they said our university has to get into legal agreement with Ford if we want the data to be decrypted, because if the data is decrypted and then there's an accident or something happens, they are not liable.
Okay, got it.
So
yeah.
It is, what I'm saying is it is possible, the technology is there, but it's only a legal issue.
Okay. So my last question is, so you know, the DSRC is now weekend, right? So we talked about the security. Before it was more secure because the spectrum was only for connected vehicles. But right now, so the spectrum is opened up by the FCC, right? They're taking steps to open it up to other industries. So they're promoting more CV2X, C vehicle to everything communication. So do you see any variation of your work if you're not able to use DSRC, or if it's not as strong as it was before?
I think the main thing is we are developing applications rather than the standards. So if the standard is CV2X, we'll just use that standard.
I see. So it will work, yeah, no change will be necessary.
Correct. I mean, the CV2X standard will not have the WSMP packets. It will have something different. Right. We'll just change the format to that packet. But in terms of concept and technology, any communication technology will work.
Okay, thank you.
Yeah, we're not reliant on any technology. We just change the onboard unit to CV2X onboard unit.
Okay, thank you.
Thank you. And you are very right that DSRC is becoming limited. I think the CV2X is becoming more popular.
Yeah.
And so at one point there was a discussion about making DSRC the standard, but I think that has changed nowadays.
Yes.
And now there is a discussion saying that there should be more than one standard.
Yeah. So I just remember one more question. Sorry. So how do you see 5G is changing? Because right now DSRC was attractive because of the low delay, right? So 5G will be able to accommodate a very low delay. So do you see our landscape is changing for vehicular communication when 5G become more common?
I think so, because there's a LTE standard which does not require the communication between car to cell phone tower. It allows car to car communication.
Direct communication, yes.
Yeah, the delay was coming from the communication with the cell phone tower. And this new standard in the telecom industry, in the LTE, that you can communicate directly with the car, actually is a strong competitor for DSRC.
Yeah, and also it runs on 5.9 gigahertz too.
Correct.
That direct communication spectrum, yeah.
Correct.
Thank you.
And also it is being run by big carriers. So there is a big interest in having the car-to-car communication based on cell phone technology.
Okay. Thank you. So there are two questions in the chat box. So Charlotte, are you going to read those?
Yes. So Jamal has asked, did you study about fatal crash reduction for each sensor when that you talked about in CAVs compared to regular vehicles?
We have not actually studied that, but our system informs all the cars around directly. It also displays a message in the DMS. So I'm assuming that those cars which don't have the wireless technology will get that message, but not in real time, not in milliseconds, but when they will be close to the DMS. Because the message may be displayed on the DMS, but the car may not be there at that time. But the cars which are surrounding and have the wireless technology, they will get the message in split second.
Okay. And then Parth has asked, are these applications available for further R&D?
Yeah, there are lots of applications which have been developed for those three categories. I mentioned the mobility applications, the environmental applications, and the safety applications. There are lots and lots of applications which have been developed by lots of people around. And I think there are websites where those applications are there, and the videos are also there,
Right.
showing how the applications are effective.
Can I add? So the ARC-IT website managed by USDOT and ITERIS. So ARC-IT, ARC.IT or -IT. So you'll see all like over 120 applications in these three categories.
Correct. And they are very nicely prepared also in one of the websites. I remember, I don't know exactly what the one Ronnie is talking about, but I mean, every application has a one page of description also.
And
what
the physical architecture,
Correct, physical architecture. I think we're talking about the same website.
Yeah. In my ITS class, I teach that. Yes, thank you.
Yeah, USDOT has spent huge amount of money to develop this connected vehicle application.
Right.
And they have been testing it and still testing it. They have tested in Florida and Michigan and all the other, many other places, California.
Yeah.
And Parth also clarified, he said he specifically was asking about the applications that you had presented.
Oh, okay. So Dr. Attiquzzaman's application, yeah.
Oh, I see. It can be used by other people, but it's not in a format or in a form that others will be able to understand it. And we're also very much tied to the hardware we had from a company called Arada. And I don't know what happened to Arada. At least our equipment still work.
I think they are sold to another company. Yeah.
Correct.
They no longer exist. Or I know. I'm not sure, but yeah.
That's my impression also. So our application is very much tied to Arada. So if others have to use our application, they have to change the application to work with other devices, other manufacturers' devices.
And then Mizan has asked, what could be the impact of environment like snow on communication for your applications? And do you do any experiments on that?
As I said, DSRC communication was built for vehicular communication, so it's very robust in the environment like fog, snow, and rain, all this stuff. So I don't know exactly how much it will be affected, but if it is affected, of course, then the communication. If the communication is affected, of course, the application cannot run. But I'm expecting that it would not be affected too much from all the papers I've read about the DSRC in fog, snow, and the rain conditions. So Mizan is asking, did you do any experiment on that? We haven't actually experimented the effect of rain, fog, and snow on DSRC. We haven't, but there are a lot of studies around.
And Zadid has asked, how fast are the OBD devices in collecting the CAN data? Is it real time? And do you use it in real time or collect the logs and post process?
It's real time. I don't know how much, probably hundreds of times a second, you can read that information. In fact, you can read the information continuously depending on the speed of your of the processor of the laptop or the computer you have on your car. You basically have to send a request to the CAN bus saying that I need this data, and it will refresh the data. So it's real-time data.
I have one more question, Dr. Attiquzzaman. So if you have multiple communication technologies on a roadway, so a vehicle is going, say where you have DSRC, but then in another location, it doesn't have DSRC, just 5G. Another location, Wi-Fi. So do you see a role of heterogeneous wireless networking so that the vehicle-based device can recognize what is available and what is the application requirement, and based on that, it switches between communication options available? So do you see that being something that needs to be developed?
Sure. Actually, this is very easy to do in terms of communication technology. If those standards are available, let's say there are three things available, as you say, DSRC and LT. Right. Switching between them is no problem. Look at our smartphones, a small thing, right? And that switches between LT and Wi-Fi as you go out of the building and come inside the building. So switching between those technologies is no big deal in terms of implementing it.
But so the vehicle is, and it is running different applications. So for some application is safety, so that is like you need information to transfer in 1 millisecond. Simultaneously, vehicle may need to run another application that is not safety critical. So there's making this intelligent decision. So do you need some type of intelligence in switching between or running multiple applications at the same time?
I think you are very right. We do need that intelligence, but that is very easy to develop. That's not a problem at all. We just measure the performance of the 2 or 3 networks which are available to us. Right. And we use the network depending on which application is requiring it.
Running sound is okay.
Yeah, and finding out the performance of a network is very easy. I mean, it's no problem. We can find out the bandwidth available. We can find out the delay. We can find all this information within split seconds.
Zadid, you're in the audience. Do you have any question on this? Because we have been working in this area.
Yes, sir. So I don't have any questions.
Okay, right. Thank you.
Yeah, one thing I forgot to mention, a lot of times people ask me how much would it cost to implement all this in a car? Because the onboard unit we purchased, they asked me how much does it cost? The onboard unit we have is $2,500. But my answer is when it will be widespread, it will be available and it will be built in by the manufacturer inside the car. It will not need the casing. It will not need any of those stuff. It will not need an extra power supply and all this stuff. It will be a small chip in the car. So it will be a matter of putting a chip in the car and a computer, computer in the sense that it will be a single board computer which has to be put in the car to process all the information. And I read a couple of reports from car manufacturers. They say that the additional cost to the car when you're buying the car would be around $200 maximum. So that is useful information because people are worried about how much the car will cost extra.
Right. That's a very good. When I worked in a car company in my sabbatical, so they said that we cannot add more cost to the car, but so if it is lower cost, then they will be willing to do it. Yeah.
Yes. So I think a lot of people will not worry too much for $200 when they see the increased safety.
Yeah. And so also some cars already have it, right? Some car companies already provide this communication interface, as you mentioned in your presentation.
Correct. But people are always worried that this thing will, whenever the government makes it a standard or mandatory, people will talk about additional cost. So that
Yes,
is the additional cost, $200 probably, or even less. I mean, as time goes along, it will probably be even less.
So if there is no question, we are close to the closing time. Any more question? We have maybe time for one last question. If no more question, Dr. Attiquzzaman, thank you so much for presenting. This is a great topic, and I also learned a lot from this presentation. So thank you so much.
Thank you very much for inviting me. It was a real pleasure to be able to share my research experience with you. If you have any questions, you feel free to email me, and we hope we can meet someday face to face. That will be more productive. Thank you very much again.
Thank you, Dr. Attiquzzaman. Thank you.